So, welcome to another exciting digital design class. We are going to continue our midterm review until your questions are exhausted. I should point out that in the other section, they had no questions because they already understood everything. Really. So, as a result, we moved on to new material in section 2. But if there was something that somebody wanted to review in the midterm, I'd be very happy to go over it. Are there any questions about the midterm? And if you don't ask me any, we'll do new material. Sure, you betcha. Question 4. Which of the following relationships represent the dual of a Boolean property? And the Boolean property is x or x prime equals 1. So let us please start by defining what is the dual. Would somebody like to take a stab at that one? What is the dual? Yeah, so dual is defined as, here's a marker that doesn't work. Let's throw that away. I'll try that again. So the dual is defined as, and here's a highlighter that doesn't look good, so we'll throw that away. Jeez. I tried a bunch of new markers today. So we take plus and we convert it into times. We take times and we convert it into plus. We take 1 and we convert it into 0. We take 0 and we convert it into 1. And that is the dual. And the difference between the dual and De Morgan's theorem is De Morgan's theorem will take x and convert it into x prime. And it'll take x prime and convert it into x. So De Morgan's theorem is just like the dual with a difference, DMT, De Morgan's theorem, because in the case of the dual, we leave the variables alone, D-U-A-L, because, right? And so this is another crappy marker. I guess it's right. So what I would say, let's switch to a pen, is that if you want to take the plus and convert it to times and the 1 convert it to a 0, what you end up with is that x times x prime must be equal to 0. And we know this is true because if x is equal to 0, then it's 0 times 1. And if x is equal to 1, then it's 1 times 0. And things times 0 is 0, unless you're in the world of quantum computers, in which case everything you know is wrong. So if this is the dual, and this is true, and that's true, the dual is true. If the non-dual is also true in general. So there is a direct correspondence between this and one of the answers in question 4. Are there any other questions about question 4? I hope I answered the question. You can find the definition of dual in the book on chapter 2. And it's been a while, so you guys probably forgot it or something. Any other questions about the midterm? Number 10. It says the expression, let's write this down. The expression A, B, C, prime prime, is represented by which of the following canonical symbols? Okay. So if you converted this into a binary number, it would be 1, 0, 0. Right? And so that is a product term which, if true when A is 1, B is 0, and C is 0, corresponds with the binary representation 1, 0, 0, and you would write that as 4 in base 10, you see. And so that's 1, 0, 0 is 4 on base 10, because 2 to the 0 is 1, and 2 to the 2 is equal to, did we do this right? 2 to the 0, 2 to the 1, 2 to the 2, right? 2 to the 2 is 4. That's good all day long. So that is corresponding to M, I should say little m, 4. And you can see how this works out, right? Because if what happens is you have a truth table, A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, that when A, B prime, C prime is true, you're right here. And if you number this, 0, 1, 2, 3, and then 4, 5, 6, and 7, you can see that this is M0, M2, M3, M4, M5, M6, and M7. And so when you look at the product term and its impact on the function, it's true when A is equal to 1, B and C are both equal to 0, and everywhere else it's false. And so that is equivalent to saying that in shorthand notation, which is equal to M4. Does that sort of make sense to everybody? It's sort of a long-winded explanation as to why it's true, which I think everyone at this point should understand. Let's see now. Capital M corresponds to max terms. Little m corresponds to min terms. So this should be a little m, because this is min terms. Little m4. There is a big M4, but that is different, right? Big M4, that's for a minimum product. So if you were having, A prime plus B plus C, that would be big M4. But if it's only A times B prime times C prime, then it's little m4. If that makes any sense. If it doesn't, tell me, and I will torture you with more explanation. Any other questions with the midterm? Sure, and there was another person who tried to talk at the same time, so what was the other question you'd like to hear? 65 and 66, you got it. So we'll have 3 now to do, 23, 65, and 66. Let's see now. All right, what do we got? There's a compelling argument here for a fresh sheet of paper. Let's do that. Because it's all big science, Let's see, somebody said... that I have an 8-to-1 mux whose inputs A, B, and C, or X, Y, and Z, whichever you prefer. Let's do X, Y, and Z because we'll just mix it up a little bit. Gives us an output called F. And the inputs, let's look at the inputs. Are alternating 0 and 1. And the question I have for you is, given this setup, what is the truth table for F? So let's start by writing out X, Y, and Z. How do you fill in the truth table? Madison, I never call on you. Madison, what should we do to fill in this truth table? Yeah, it's out. Oh, you bet. That's exactly right. So now, what would be a convenient way to describe the function f? If you have any doubts, you can always do a K-map. And it looks to me like we can number the truth table. And it seems to me like all the odd numbers. And the others are even. Now we can loop the odd numbers. And now you tell me, what does f equal? Yeah, f equals z. And that is the simplest possible implementation for the truth table. That is a minimal sum of products. And it is also one of the select answers that you can use for this particular question. So how did we do this? We took the inputs, we mapped them into a truth table, we numbered the truth table, we wrote out the K-map, we looped the K-map, we got a minimal sum of products, and then we found it as one of the answers to the question. So in fact, we don't need an 8-to-1 multiplexer. What we need is a wire that connects Z to F. And that wire is your simplest possible implementation for the given truth table. So I've replaced an 8-to-1 multiplexer with a wire, which is probably faster by a lot. Any questions about this homework question? Oh, sorry, midterm question. Midterm question. Question 23 that was. Everybody good with this? On to the next one. So the next one was going to be 65. And I just use this paper here. 65 says, write the 2's complement for the 5-bit binary number in base 2. How do we find the 2's complement? First check it's a 5-bit number. Yes, count 5. Yep, 5. Anybody want to, let's see, Evan, you're hardly ever called on. What should I do to find the 2's complement? I'm sorry, you're hearing music? Oh. I was going to say, if you hear music, something's wrong with Zoom. Yeah, 2's complement. Here's a 5-bit number. Let's get the 2's complement. There you go. That is exactly right. And so now I have 1, 0, 1, 1, 1. And that is equal to minus 5 using 2's complement base 2. And that is a correct answer. You will find that as one of the selections. Any questions about 2's complement? You guys, I've been hammering you with 2's complement. I'm surprised. I figured you'd know it by now. So here comes another question. It's 66. How do I find the 2's complement again? Is this the same question? No, this is... Oh, it's a 5-bit binary number. Okay. So we start off with 0, 1, 0, 1, 1 in base 2. I think I should leave this as an exercise for you guys, because at this point now it's obvious how you formulate the answer. So I'm going to let you guys do this one, because otherwise I'll be doing the whole darn thing for you. So yeah, you should, given this example, I think you can do the next one on your own. Let's get another question in here. Any other questions? Midterm questions? You got it. 32. Let's have a looky-loo and see what we got. Okay. 32 says we want to compute 7 base 10 minus 1 base 10, which is normally equal to 6 base 10. We want to do it using 2's complement, assuming only 4 bits are available to represent the numbers. So here's an interesting thing. 7 in base 10 is 1 base 2, but if you're using only 4 bits, you must have a leading 0 of 0. Right, a leading bit of 0, because this is a positive number. And that is equal to the binary representation in 2's complement with a sign bit for a 4-bit quantity representing 7. And you needed that leading 0 to represent the sign. Similarly, if you're trying to form the negative of minus 1, you would take 0, 0, 0, 1, because it's a 4-bit number with the leading 0 showing the sign. And then what you want to do is complement and increment. So you complement and you get 1, 1, 1, 0, and then you increment and you get 1, 1, 1, 1. Looks counterintuitive, right? But that is equal to minus 1. So 1, 1, 1, 1, base 2, 2's complement representation of negative 1. Now we add it. And we get 0 carry the 1, 1 carry the 1, 1 carry the 1, 0 carry a 1, which falls on the floor, and then 0, 1, 1, 0, which is the representation of binary 6 using a 4-bit quantity with the leading 0 showing that this is a positive number. And that is a correct answer, which you will find as one of your alternative answers in the midterm for question 32. How's that grab you? So now you can do subtraction, right? This is important. And in fact, we just had a whole pile of homeworks on this one, so you guys should be expert by now. Any other questions about question 32? Was it clear? How about other questions about the midterm? Yep. Let's have a looky-loo and see what we got. Okay. Didn't we do this already? This is looking awfully familiar. Okay. So this is the multiplication tables. And what you want to do is A1, A0 times B1, B0. And we're going to have 0 times 0, 0 times 1, 0 times 2, 0 times 3, 1 times 0, 1 times 1, 1 times 2, 1 times 3, and then there's going to be 2 times 0, 2 times 2, 2 times 3, and we'll have 3 times 0, 3 times 1, 3 times 2, 3 times 3. So given the complete multiplication table with all possible iterations. I write 0 times 0, 0 times 1, 0 times 2, 0 times 3, 1 times 0, 1 times 1, 1 times 2, 1 times, oops, 3, 2 times 0, 2 times 1, 2 times 2. Why isn't it saying 2 times 3? That should be 2 times... Oh, I forgot 2 times 1. I should just number this in binary. Let's do that. That's better. A, B. How's that? Right, because 0 times anything is 0. 1 times anything is itself. And 2 times right, because 2 times 3 is 6. And 0 again. And that's going to be 9. And that's 3 times 2, which is 6. That's 3 times 1, which is 3. And that is correct. So let's take a look at C3. C3 is equal to A times B times C times D. Or A0 times A1 times B1 B0. And if you then proceed to do the reverse engineering for the diagram, you will see that that is indeed the case. Similarly, you can do something involving C0. In fact, if you like, you can make a K-map out of C0, number the rows, and write down radix is equal to 10, just as you're numbering the rows, and then fill out a K-map. And it's just like every other K-map you've ever done, with a difference. And the difference is how you label things. So what we'll do is we'll put in the C outputs over here. And then if you want to fill in C3, well, we already did C3. So you'll do C0. I'll grab a pen. And we see 5, 7, 13, and 15. Right? And now I can loop the K-map. And C0 is equal to, you tell me. I could say F is equal to, put it that way, F is equal to, because that's going to be your function right here. Maybe the inputs should have been A0, A1, A0, that would have been better. A1, A0, B1, B0. Then you can write C0. There, that makes it more consistent. So now you tell me, what should C0 be? Yeah, it's A0, B0. And knowing this, you should be able to reverse engineer to see there's one AND gate and it's on A0 and it goes to B0. And that gives you C0 output. So that's fine. You can do the same thing now for C1 and C2 and reverse engineer it using your K-map and verify whether or not this is a 2x2 binary multiplier. Just because you know what a 2x2 binary multiplier should be, when I wrote A, I meant A1, A0, B1, B0. So these are the independent variables. These are the dependent variables. And when I do a K-map like this, I'm getting the minimum sum of products. So I can do that trivially here for C3, but that's because everything is 0 except for the last row. But the other stuff's not so trivial, so I'll do K-maps for each of those, get minimum sums of products for each of these, and then I can compare it against what we have in the schematic diagram. And that should give us an answer as to whether it's true or false. How's that grab you? Is that all right? So what else? What other questions do we have for this midterm? No other questions? This is due in, when is this thing due? Next week? I think we got a week. Yeah, sure. Let's go over this. See, this is the midterm and it's due on the 29th and today is the 22nd. So you've got time to ask more questions if you need more questions to be asked. Let's look at question 30. Isn't it funny that the second section didn't have any questions? Which of the following binary multiplications is correct? Well, you can do this a couple of ways. You could convert all the binary multiplications into decimal and then multiply them. I like that. That's cool. I like that. Is it cheating? I don't think so. I mean, you could sit there and do binary multiplications till you're blue in the face for all I care. I don't care. It doesn't bother me. How many different ways can you do this? Well, I don't know. Somebody said, is 1101 base 2 times 1011 base 2 equal to blah, 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 blah. So what's this in base 10? Well, that's 8 plus 4, which is 12 plus 1, that's 13. And this is 8 plus 2, which is 10 plus 1, which is 11. And I can multiply these things because I get a number, right? And then if you wanted to, you could take the number on the right-hand side base 2, and then convert that over to base 10. That's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7. 2 to the 7 is 128. And then this number here is probably 15. And add that over, and you get 143. And look, it's the same. See? The same. They're the same. So that means, yes, it worked. Yes, indeed, it worked. Or you could do it the long way and just multiply these two numbers out and then get that number. So I provide you with your choice of how you want to get the answer. Multiple choice questions don't know how you got the answer. Any questions about question 30? Sure thing. Sure thing. Any other questions about the midterm? Hearing none. Hearing none. I shall proceed to cover new material. Yay! And away we go. In today's lesson, we're going to learn how to count to 3. And if anybody talks to their parents and they say, "What did you learn today?" you can tell them, "I learned how to count to 3. This is chapter 6 material. So let me illustrate how this works. 0, 1, 2, 3. This is a little embarrassing, but that's the way you do it. This is how you count to 3. And this little bubble diagram showing the different states and their values, this is called a finite state machine. In fact, it's a degenerate finite state machine, sort of like the degenerates that hang around all summer near the drugstore going, "I've got to do something today." Those degenerates, like that. Only here, it's degenerate because it's specialized, and it is what they call a counter. What does a counter do? It's like Sesame Street. It's the count. I love the count. So here is the counter, and what we want to do is build some hardware that implements this counter so it can count amazingly fast, faster than any computer program you can write. So let's see if we can do that. We'll start by postulating that we have a device, and this device will store 1 bit of data. This is our first little bit of memory, Q and Q prime, and this is known as a delay flip-flop. And the goal of the delay flip-flop, which has a little clock going in, is to latch on an edge of the clock, either rising edge or falling edge, it doesn't matter which, there are both kinds available. To latch on the rising edge or falling edge, whatever is present, either a 0 or a 1, on the input to the delay flip-flop, and it will hold that data. So this is 1 bit of static RAM. So this is actually a memory element, and that allows us, and I will show later in the course how to build these things, and we'll just beat a dead horse on this, but first you have to read about it in chapter 6. This enables us to build counters like that. And what we do is we create what's called a present state next state diagram, which captures the counter. And this is the simplest possible first example I could contrive. So we'll start in this way. A and B. Well, I know. Yeah, let's do that. A and B. And then the next state will be called A plus and B plus. And this will be the present state, and this will be the next state. So PS is present state, NS is next state. And I'm just going to write down some numbers here. 0, 0, 0, 1, 1, 0, 1, 1. I'm counting. And now the next state, if you're in state 0, is going to be 0, 1. And the next state, if you're in state 1, is going to be 1, 0. This sounds trivial, but it becomes less trivial as you get to more exotic diagrams. So we go through this formalism. Bear with me. So here we are in state 2. Next state is going to be 3. Now here, we're in state 3. What's the next state? Well, according to this, we go back to state 0. And that is that. That is our little present state, next state diagram. Now, having done that, we can proceed to determine what the so-called remapped excitation tables will be for the flip-flop of choice. Right now we only know one flip-flop, but soon we'll know 4. So we'll start with the input, and this will be called A, and this will be D sub A. So what we'll do when we write A and B is we'll assume it means Q sub A and Q sub A prime, and this will be A plus, so that'll be the next state after we latch our little square wave. So let's look at what the inputs need to be for D sub A and D sub B. These are the inputs to flip-flops A and B. So we need 2 flip-flops for 2 bits. This is a little 2-bit counter. So the input needs to be the same thing as what you want for the next state. So we can just copy. This is why I start with D flip-flops, because all you have to do is copy what you want for the next state, and that's what it will be. So in other words, if I put a 0 in to D sub A, and then along comes, a rising pulse, it'll latch the 0. If you put a 1 in to D sub A and rising pulse comes in, it'll latch the 1. So 2 flip-flops, no waiting. And now that you know the remapped excitation table, and they call it an excitation table because it's so exciting. So if you look at, by inspection, what D sub A is equal to, it's equal to A exclusive OR B. And so you can write that. D sub A is equal to A exclusive OR B. For more complicated truth tables, you will need to do a K-map. And then here's D sub B, and it's equal to B prime. So now we can write D sub B equals B prime. And now that we have these 2 equations which capture the remapped excitation table as a function of the present state, we can finish building our counter. Our implementation, our design, will kind of look like this. 2 counters, A prime, B prime, D sub A, D sub B, with a little counter clock thingy going in. And it says here D sub A is equal to A exclusive OR B. So here's B, there's A. All I need is an exclusive OR with inputs A and B. And I'm not going to draw the wires because it makes things look messy. But I can assume you can draw a wire from there to there and from here to there. And then D sub B is equal to B prime. That's right there. Take this, run it over there, and it will alternate from 1 to 0, 0 to 1. So just put B prime in, and bang, you're done. There's your counter. And it will count 0, 1, 2, 3, 0, 1, 2, 3. And it will do it in about 3 gate delays. How fast is that? Well, gate delay could be single-digit nanoseconds. Could be picoseconds. Could be femtoseconds. How much is that? Well, femto, that's 1 times 10 to the minus 12 seconds. How do you build an AND gate that switches in 1 times 10 to the minus 12 seconds? Well, believe it or not, they've done it already. What you do is you get a laser. This is an optical implementation, or I should say a photonic implementation, and the laser cavity is fed by other lasers. And when it gets to a critical point and all the legs start to energize the cavity, it will then proceed to laze in the other direction, and it allows you to make a femtosecond switching time AND gate. And yes, you need an optics lab to do it. And yes, it takes as much space as an optics bench, or at least it did several decades ago. But here in the new age, maybe they can make them smaller. In any case, you can, in theory, make your AND gates go as fast as you like. And if you're using light, you're not restricted by things like, I don't know, the speed at which electricity goes, because that's slow compared to light. Maybe 8/10 the speed of light. This could be switching much faster. So this is an interesting idea, because now we can build counters that count in all sorts of interesting and wonderful ways. But before I go there, I would like to open the floor to questions about our first counter. Our first encounter with counters. Ooh, that's a good one. See what I did there? Encounter with counters. Any questions? Want to see another example? Let's do another example, just because it's so much fun. So this is what they call, before we were doing combinational logic, but because we've got a little memory element in there, we call it sequential logic. Everything was running in 3 gate delays. Here, we can count up to very large numbers, which take a long time to do. Let's do another one. 3, 2, 1, 0, blast off. Okay. First step, present state, next state diagram. So here's A, B, A plus, B plus, present state, next state. Now if I'm in state 0, my next state is 3. If I'm in state 1, next state is 0. This is why we write these things down, because it's a little bit confusing now that we're counting backwards. When I'm in state 1, next state is 0. Sorry, this is state 2. Next state is 1. It's a good thing I'm doing this. Jeez. When I'm in state 3, the next state is 2. And now I have to do my remapped excitation table. And it's trivial now, but it won't be. D sub A, D sub B. And now, if this is what you want for your next state, that's what you use for your input. And now we can look at it again. This time it seems as though D sub A is just like it was from last time, only with a difference. It's the inverse exclusive OR what you might call A exclusive OR B inverse, also known as exclusive NOR. And then D sub B is equal to, and you take a look, it's no longer B prime, it's just, oh yeah, it is D prime. That is D prime. So it's still B prime, B prime. So now I've got to get my implementation happening. D sub A prime, D sub B, B prime, and then D sub A is equal to A exclusive NOR B. So I write A, B, just like before, only with a difference, and the difference is I get a little bubble on the output that makes it an exclusive NOR. And then B is equal to B prime, and this time around I'll just draw a wire. There. That makes it equal to B prime. And that's it. And that's my implementation. What do you think of that? Let's do it again. Only this time, I shall postulate yet another flip-flop. And this one, again, right out of the book, it's called the toggle flip-flop. Toggle flip-flop is different from a D flip-flop. Toggle flip-flop says if the input is 0, the next state equals the present state. So we just copy the next state to the present state. But if it's 1, then the next state is equal to the inverse of the present state. So in other words, if you just left it as 1, and then you ran a clock signal in there, it will change from 1 to 0 and then 0 to 1. Basically, you built a buzzer. So the buzzer effectively allows you to toggle this back and forth. Knowing that, now if I want to re-implement my counter, I can still write the present state and the next state. Just like before. Zero goes to 1, 1 goes to 2, 2 goes to 3, 3 goes back to 0. But now it's T sub A and T sub B because these are toggle flip-flops, not D flip-flops. So the remapped excitation table is fundamentally different, and we're no longer just copying the next state over into the inputs. Instead, we're saying, look, if T is a 0, we keep what we had. So here it looks like there's no change, so we put in a 0, but here we do have a change, so we put in a 1. Here there's change, and there there's change, so they're both 1. Here there's no change. Here there is a change. Here they both change. And look how things have changed now. T sub B equals 1. It just means it's toggling. T sub A is equal to, looks like it's equal to B. Look how much simpler the implementation is now with toggle flip-flops. I don't need an exclusive OR. T sub A, T sub B, T sub B is equal to 1. T sub A is equal to B. Look at that. I now have a counter implemented with toggle flip-flops that's totally simple compared with what we did before, because look what we had to do before. I needed an exclusive OR gate to make it work. But now, all I need is a wire and a constant, and I'm done. So the design was a little bit harder, but the implementation was cheaper, simpler, and faster. Right? Because look how much things would slow down with a exclusive OR. That's an extra gate of delay. Whereas here, I don't have to worry about that. I don't need an exclusive OR to slow me down and take up space and make things more costly. Who got confused? Be honest. Anybody confused by this? It's counters. How exciting. We're counting. So now, let's do another example. Let's assume that I'd like to use my toggle flip-flop. One, 2, 0, 3. We're going to make a wacky counter. Okay. So now we've got the present state and then the next state. That's A, B, A plus, B plus. So if I'm in state 0, next state is 3. If I'm in state 3, next state is 1. If I'm in state 1, next state is 2. If I'm in state 3, next state is 1. If I'm in state 1, the next state should have been 2. If I'm in state 2, the next state should be 0. Somehow I got things messed up here. So from 0, we go to 3. From 1, we go to 2. From 2, we go to 0. From 3, we go to 1. So now we take a look at this, and what we see is we didn't do the remapped excitation tables yet. So let's do d sub a, d sub b. So d sub a is going to be 1, 1, 0, 0, and this will be 1, 0, 0, 1. So from inspection, I can see d sub b is equal to a exclusive or b inverted. D sub a is going to be equal to a prime, right? Because there's a, and here's d sub a. So that's one implementation. Let's keep going. Let's look at a different implementation, t sub a, t sub b. Now I've got two flip-flops. I can compare the implementation costs for each. So t sub a is going to be a 0 if there's no change. T sub b is going to be, t sub a will, toggle inputs will be 0 if there's no change, and they'll be 1 if there are changes. Here I see there's changes for both. Here I see there are changes for both. Here I see there's a change for the most significant bit. And here I see there's a change for the most significant bit. No, the most significant bit. And so now t sub a equals 1, and t sub b is equal to a prime. This is still way easier than that. And so now if I want my implementation to be the simplest possible that I can get, I just make that a 1. And t sub b equals a prime. And now I have my little counter going 1, 2, 0, 3, 1, 2, 0, 3, 1, 2, 0, 3, all day long. Fast as it can. And this is a simpler implementation for toggle flip-flops than that. The design was harder, but I got to compare the two designs and I could check. I don't need an exclusive NOR gate because I used a toggle flip-flop. How does that grab you? Now let's do it again. This time we'll do 3, 2, 1, 0. And we'll do present state, next state, and the 0 goes to 3, 3 goes to 2, 2 goes to 1, and 1 goes to 0. And now we'll use t sub a and t sub b, and we'll see 1, 1, and now I have t sub b equals 1, and t sub a is equal to b prime. I don't have to bother drawing it now because once I have these equations, the implementation becomes relatively trivial. But I guess I could draw it, because what the hey, right? sub A equals B prime. T sub B equals 1. And you can see the implementations are pretty similar in complexity, but the finite state machines that they create are different, really different, right? Because 1203 is totally different than 3210. So what do you think of that? Toggle flip-flops, huh? Pretty slick. And D flip-flops. D flip-flops are 1 bit of dynamic RAM. And they're static RAM. They're static because they don't need a refresh. Dynamic requires a refresh. We use capacitors for that. We'll talk a little bit more about dynamic and static RAM later. Any questions about this? So you guys are going to be doing this when you start doing, I guess it's homework number 8. Edit the test. Let's have a look. All right, so what you get is called characteristic equations for the flip-flops. And Q plus is equal to D is the characteristic equation for the D flip-flop. And you can arrive at these things with relative ease because you've got to have a present state, Q, and the next state, Q plus. And you have to know what the input should be in order to arrive at these things. And the answer is for the D flip-flop, it's 0, 1, 0, 1. And so now it's pretty clear. Q plus is equal to D. Similarly, for the toggle flip-flop, T, you can look at the inputs and say it's 0. That won't change anything. Here you want the input to cause a change. Here you want the input to cause a change. Here you want the input not to cause a change. So now you can write the D, let's say T, for Q plus. And you can write this a few different ways. I guess the way to really write it, I guess, is be this way. Suppose you had a stimulation input and the present state. What would the next state be? There's a couple ways to write it. So here we say, the next state doesn't change, next state doesn't change, the next state does change, here the next state will change. And so now you can write Q plus equals, and then here's the expression for T exclusive or Q, which is equal to T prime Q or Q or TQ prime. So that gives us an ability to derive the characteristic equation based on the behavior of the flip-flop. Similarly, you could say D and Q Q plus is going to be 0, 0, 1, 1. And that's how you get Q plus equals D. So that's pretty cool, actually. That gives us an opportunity now in order to be able to derive the expressions for other kinds of flip-flops. And so now what we'll do is we'll try and use it to create what's known as the JK flip-flop. So what we'll do is we'll write out J, K, and Q. And we'll characterize the JK flip-flop into 4 separate areas. The first one we'll call the hold state. The next one this is called set, and that's called reset. So then what we'll do here is we'll call this the reset state, and we'll call this the set state, and then we'll call this the toggle state. In other words, stimulating both K and J, K and J at the same time with a 1 causes toggle behavior. It begins to look like a toggle flip-flop. So in hold behavior, when you look at Q+, based on the JK flip-flop input, what happens is Q is in hold state, 0 and 1, doesn't change. Here, reset causes it to go into the reset state, so whatever it was, it turns to 0. Here, set causes it to go to the set state, so whatever it was turns to 1. And here, toggle causes it to change states, so if it was a 0, it becomes a 1. If it was a 1, it becomes a 0. That's the toggle. And now, we can come up with Q+ based on the K-map. So I number my truth table, number my K-map, and then I can fill in my truth table. Oh geez, I got a call. I'm sorry. Ignoring that. 0, 1, 0, 0, 1, 1, 1, 0. And looping, loop like this. And that gives me J, Q. And then I can loop like this. And that's going to be K prime Q. That should set 0 and 1. So that should be JQ prime. JQ prime or K prime Q is how you describe the characteristic equation based on the behavior of the JK flip-flop. So that's pretty cool, actually. And what that does is it enables me to use yet another flip-flop for my design. So let's go back to the counter with our new knowledge about JK flip-flops. This is exciting, isn't it? 0, 1, 2, 3. Let's design a counter that uses JK flip-flops. So we start off the same way. We've got a finite state machine diagram that describes the specification for the hardware that we need to design. And then what we do is we write out the present state, next state table, just like we did before. I guess we should use A, B, A plus, B plus. So 0 goes to 1, 1 goes to 2, 2 goes to 3, and 3 goes back to 0. Then we'll have J sub A, K sub A, J sub B, K sub B, because we need 2 flip-flops, and JK flip-flops have 2 inputs. Before, we were dealing with D flip-flops, which had only one input, or T flip-flops, which had only one input. But now we have J sub A, K sub A, whose output is A and A prime. And then we have yet another flip-flop, J sub B, K sub B, and B or B prime. So that's very interesting, right? Because now we need the remapped excitation table for the present state, next state table for the two flip-flops, JK flip-flops. So we're still trying to count to 3, but now we're using different flip-flops. And it looks to me like this has got to be in a hold state. And what we remember from hold state is that J and K can be 0, 0. So that'll work. But if you want to, you can also say it could be in a reset state. So now comes an interesting point. You know, how do I back out what the possible inputs might be for the JK state given Q and Q plus? In other words, suppose we go the other way. Q, Q plus, 0, 0, 0, 1, 1, 0, 1, 1. These are all the possible combinations between the present state and the next state. What can J and K be? Well, here we want it to be either reset, which is over in here, or we can say hold. So that means it's 0, don't care. Why? Because if you assert the reset line to be true, it'll set it to 0. But since it's in a state that you already want, where it's 0, we don't have to care. So that's kind of cool, actually. Right? In other words, ending up with the next state being 0, there's choices. It's either you put it in the reset state or you put it in the hold state, especially if it starts with 0. And then if you want it to be set, well, you can either say, well, I'm going to toggle, or I'm going to set. So in this case, it doesn't really matter if you say, I'm going to put it in the set state, just as long as you don't assert reset. So if this was 1, 1, it would cause a toggle. But if it was 1, 0, well, what would happen? It would set it. So at some level, we don't care what happens in the in the K sense. And then comes, did we get that right? 0, 0 should be 0x. 0, 1 should be 1x. Yep. And then 1, 0 should be x1. And then 1, 1 should be x0. Why? Because if you want this to be set, you can either say set, or you could hit 0, 0 and make it a hold. In this one, you want it to be reset. You can either assert the reset to be true, or you can say 1, 1, make it toggle from 1 to 0. So that's your choices. And so knowing these don't cares are here is kind of important with respect to what it is you might like to do. So if you take the remapped excitation table for the JK flip-flop, and you write it out in this way, what you get is really rather interesting, because you can now see you're changing from 0 to 0, so you can put in 0x in here. You change from 0 to 1, and now that is a 1x. Change from 0 to 1, that's 1x. Change from 1 to 0, that's x1. Change from 1 to 1, and that's x0. Change from 0 to 1, we're back to 1x. Change from 1 to 0, and that's x1. And now the remapped excitation table says, simplest thing you can do for K sub B is just make it a 1. Simplest thing you can do for J sub A, J sub B is also make it a 1. So you can tie these together and tie it to 1. And now it's a toggle flip-flop because you've made them both assert as 1. J sub, let's see now, K sub A, we could probably set it equal to B. And J sub A is the same as B prime. And that is how you implement your up counter with a JK flip-flop. And if you think about it, that was a rather more difficult design than, let's say, the toggle flip-flop, the design procedure. But the implementation was certainly no more complicated. Well, hardly more complicated. Who got confused by this? Be honest. So let's take a look at some of the reading that you need to do. So we're in chapter 6 now. Which is called Sequential Logic Design, chapter 6. And that is on page... Does it show it? You can't see, can you? Huh, isn't that funny? That's on page 263, I think it says. Well, I got the light shining in my eyes, and I can't see the glasses. But, why can't I see my glasses? Oh, because they're covered by the scrap paper. Let me grab the glasses so I can see what page number we're on. It says 283. And so you're going to want to start reading from 283 out through, and you can see here's the JK flip-flop, which we just covered. We'll do the RS flip-flop next time. We won't have time for that. No sense rushing. Let's see now. They'll talk about D flip-flops. So here's a little section on D flip-flops. So you're going to be all the way out through page 299. And then they get it into these interesting characteristic equations on page 307. So here are some of the characteristic equations we have derived already. We got the JK flip-flop, we got the D flip-flop. I didn't really do the, I guess we could do the characteristic equation for T flip-flop for next time. So that'll be part of what we'll cover in our next exciting digital design class. It's a beautiful day out. Hope you go out and enjoy the day a little bit. Don't forget, you've got a midterm coming due. Don't wait till the last minute to submit it, because, as you know, Blackboard is brutal with regard to cutoff dates. It won't let you submit afterwards. So, just in summary, today we did D flip-flops, T flip-flops, and JK flip-flops. We did characteristic equations, and we did counter design. So we did a lot, and we reviewed for our midterm. All very exciting. Look out, I think there might be learning happening. Or at least I hope there is. So enjoy the rest of the day, and thank you very much for your attentions. Thank you. Thank you. Thank you.